Hi, please excuse me sitting down. I need knee operation or two. Um, my name is Ruth Bamford. I'm part of the Rutherford Appleton Laboratory in Oxfordshire. I'd like to talk to you about our recently funded project called AEGIS, which is to do with electromagnetic shielding. Something that's not really been discussed much today, or indeed during the rest of the week, is the what's often described as the look of Apollo. Here plotted are the solar proton events that occurred during the period of Apollo, and those are the timings in blue of the Apollo missions. And for most of them, they were outside the Earth's magnetosphere. And if you overlay this with the standards for the International Atomic Energy Workers, you can see that in particular, the one that between Apollo 16 and 17 is been of great concern to all the space agencies, the manned program, and in fact has been used as somewhat of a yardstick for warning. Now, since I first saw this plot, it's been pointed out to me that the horizontal lines from the International Atomic Authorities assume immediate medical assistance, such as blood transfusions. Now, that might be very difficult if the astronauts are exposed. They won't necessarily be able to get that. So those lines should probably be lowered. But with that context, the hazardous particles we're talking about in particular, for which we don't directly have a solution, are the high energy ions, protons and large heavier ions at even higher speeds. And because above 30 MeV, they go through a standard spacesuit, and above 100 MeV, they'll go through the wall of any spacecraft that we have. So one of the approaches that's been suggested time and time again is about electromagnetic shielding. This would, if it comes to pass, will be a complementary type of technology to passive shielding. It's in no way a replacement. And basically what active shielding is using electromagnetic forces to deflect or retard the charged particles. And there have been numerous studies paid for by the space agencies. But one thing that they've all had in common, these projects, is they've all looked at the engineering of how you put a big magnet or a big electrostatic field in space. That's not what the AEGIS project is about, because it has its origins looking at magnetospheres, which is actually how magnetic fields interact with the solar wind. Now, we know that the Earth gets some of its protection from its magnetosphere, and that places like Venus do not. But so the big question is does a magnetosphere have to be the size of a planet to work? We know that on the moon there are anomalous magnetic anomalies, which crustal magnetic fields, which are very small, intense, and relatively, well, depends on what field you're in, whether you call them large magnetic fields or small. They're still small by terrestrial standards, about 300 nanoteslas at the surface, 300 to 500 nanoteslas, and they extend a couple of hundred kilometers maybe, certainly on the near side. And these have been observed by numerous spacecraft to form mini magnetospheres, is where the name comes from. And below many of these these mini magnetospheres, we know that there are lunar swirls. Now, the connection between lunar swirls and the mini magnetospheres going on above them, I think, is quite well established. And the question is, can we improve upon these natural features for an artificial system? So the team I've been involved in, as we've done many papers on the analysis of the natural mini magnetospheres. They form a great database because of the number of missions that have flown through them, the type of plasma instrumentation on them, and they act as, if you want to think of it in a different way than you probably generally think of it. It's like having a big experiment, a lab experiment in space, because you've got a fixed footprint that doesn't change, although that solar wind changes and the geometry changes as the moon travels around the Earth, in and out the Earth's magnetotail. And so we've done extensive studies, we've done models, we've even done laboratory experiments there where we created scaled down mini magnetospheres in the lab, which you could photograph with your phone in what you could describe as a solar wind tunnel arrangement. So in the same sense that aircraft, for instance, might be first modeled in a scaled down version in dimensionless parameters in a wind tunnel, we did the same for a plasma wind tunnel. And the story, I think, now is quite clear about the association of what's happening above the crystal magnetic anomalies is helping form the lunar swirls, and parameters such as the generated electric fields, which I'll show you some examples of these being formed above them, are helping with the backscattering of particles that are seen on various spacecraft. So now for the application of this science, and this is what the AEGIS project is. It's an ESA-funded GSTP, which is a DRESC project, which is to look at the feasibility of a portable mini magnetosphere for potentially the gateway or a moon base or a vehicle on transit to Mars. So how do you make a magnetosphere artificially? Well, there are two ways. Firstly, you can make it like a comet, which is by releasing elements that ionize in high density. The second way is the way it probably first came to your mind, which is to use a magnetic field. These are respectively called an induced and an intrinsic magnetosphere. And of course, if it's an artificial system, you have the choice of doing both. So this won't mean anything to anybody who's not a plasma physicist, but it's important with the scale sizes of these objects that you use the right code. And we're using a particle in the cell code that's extensively used in laboratory physics. And this is the scenario for the simulation. Here we're just releasing an ion. We're actually releasing a gas of xenon in the middle of the simulation frame in an environment of the solar wind. Now, although I've only shown the protons here, it consists of protons and electrons. And xenon was chosen relatively arbitrarily, but chosen on a basis of it's a commonly available gas. It's released through a lot of thrusters, and its interaction with materials of the vehicle will be quite well known. So these should be two movies that run simultaneously. Can we get the other one to run? You on the panel? No, I don't know if it'll run. Oh, it'll run if I do that. So here what you're seeing is essentially a tsunami or a CME type wavefront enveloping the vehicle. And in defense of this, the spacecraft is releasing the xenon. And what it's doing is forming a diamagnetic cavity in the solar wind. This type of experiment, if you think is completely theoretical, it isn't. It was first done artificially in the 1980s with the AMPTY releases. If anybody's here old enough to remember them. And in fact, this work has its origins as a result of analysis of those events. Now, here's a still frame of the more of the parameters. So you've got on the top there, the particles, at the bottom below them in green, you've got what the electrons are doing. Over on the top right, you've got the magnetic fields, and on the bottom right, you've got the electric fields. Now, when you saw this as a movie on the previous slide, you'd seen that you started off with no magnetic fields and no electric fields. The importance of the PIC code that we used is it's completely self-consistent. So it allows for motions of the charged particles to form their own electric and magnetic fields. And it is this motion and this interaction that's creating these structures, which are what is forming the barrier. And we have a theoretical understanding of where these come from. And it's, for anyone who wants to take note, it's the pond motive force. Though if you look that up in Wikipedia, it'll probably say it's just associated with lasers, but that isn't actually true. What we want to do now is extend this by adding a magnetic field, because as you can imagine, if you just release a gas to defend against an SEP, two things are likely to happen. One, it's likely to diffuse away very quickly or blow away. So the way to inhibit that would be to put a low intensity magnetic field to confine and control your plasma. And when we've done some initial simulations of this, and then included some high energy particles, which didn't run as a movie. That's a movie there, that main box. Thank you. Anyway, what you'll actually see, 3,000 particles were sent into the simulation box. The plasma has been removed for clarity. That 94% of them were deflected away from the environment where the spacecraft will be located that's generating them. And to translate the dimensionless units into real units, that's as if they were 200 MeV protons from a background plasma at 1 keV, which is not probably what you would expect it to do. Now, to be effective, this is going to work at much higher energies, but the amount the magnetic field has to be is only about 100 nanotesla at the point where it forms the collisionless shock. And some initial investigation into practical engineering structures that might produce such a field have suggested that the power could be as low as 16 kilowatts, which have rounded up to 20. So you're talking about kilowatts, not megawatts, in order to do this. But I would anticipate the first stage that we'd want to do for our experiments is to start doing repeats of the AMPTY type experiments for a multitude of reasons from the gateway, but for this reason as well. And that I want to also advocate for more data from anyone who's planning on landing underneath one of the lunar swirls, so that we can look at the higher energy spectrum from the natural phenomena, and also look at the other parameters. And with that, I'd like to thank you very much.
We have room for one or two questions.
Thank you. This is absolutely fascinating. I was wondering if there are general estimates on how much, for instance, xenon would be needed to protect a facility like a moon base or a gateway station against a typical solar burst, a typical CME.
It's very low density. You don't need a lot. It's a fraction of a gram. I'm not at the moment advocating necessarily for a moon base, because I'm sure that it's a pollution starters, and hopefully they can go underground if there's an SEP. But for the gateway or an interplanetary vehicle, there's no hiding. And we've yet to discover the full consequences of SEPs, not only for manned missions, but for unmanned. And this is looking like a very active solar maximum that we're approaching. And for most of the technologies discussed this week, the engineers will not have experienced this. So one big storm could knock out everybody.
Thank you. Yeah.
That's a cheery thing to say on Friday. Sorry, I've got the other mic.
That's okay.
Hi, so I was just wondering to picture this. Is this envisioned to be something that's supposed to be continuously operating, or is it possible to only activate it when there is some indication that there's going to be a risk?
I would see it much more as a storm shelter. Unless you could run it for very little power, I still think it's going to be a significant amount of power compared to not doing anything. But for some of the largest storms, it could be the difference between literally life and death, because an SEP, the energies penetrate deep into the body, and you get organ failure, and it takes about 4 days, which is just about enough time to recall the astronauts from the gateway. But we have yet to really discover how much of a risk it is or not. But no, I don't see it as operating continuously. Unless we're all living in the world of the expanse or something like that.